yeah, I'd just like to, acknowledge off the bat that, everything you'll see here is part of a, large collaboration group. We work with a lot of people, both at national labs, universities, international universities as well. So it's pretty fun to, combine a lot of these theoretical efforts with experiments and ultimately see some of these things come into real life. All right, next slide, please. So a lot of the work you'll see today is, contributed by a lot of people here, ranging from, experiments, machine learning, first principles, DFT, and data as well. So next. So kind of the central theme of this talk is that we hope that better hydrogen energy materials will improve energy security and mitigate greenhouse gas emissions. Next. So there's this really interesting graphic on the Energy Information Administration that shows the energy breakdown between where the US generates its energy from and where it ultimately consumes it. So if you click a few times here, maybe. So yeah, the energy demand in the US is only about 35% electricity, but 65% fuels right now. But if you look at the amount of renewables we're adding, it's 90% electricity and 10% fuels. So there's a huge issue there. Not only that, the total amount of renewable energy we're adding barely keeps up with the increased energy demand. So even if we were to 10x our current renewable additions at this ratio, there would still be 65% of our energy demand that we couldn't do anything about. So the question is really, what are you going to do about all the nearly half of the transportation sector that is not light duty vehicles, total 15% energy demand? Are you going to electrify all the trucks, all the sea vessels, all the airplanes? Seems unlikely. Even bigger problem is all the industrial applications where 35% of demand is consumed by chemical production, steels, cement, ammonia, you name it. While there's a lot of efforts to electrify these, the question is really, is that going to be happening in a reasonable time scale or not? So that's why the DOE is kind of interested in hydrogen. Next. So we need to do a lot more materials development for these hydrogen energy materials, but the problem is that experiments and first principles calculations are pretty costly. So I'll talk about two applications today. Generally, metal hydrides, you expose them to hydrogen environment and they go through some kind of phase transition, allows you to absorb a lot of hydrogen at a step pressure. Experimentally, we can measure these and back out the thermodynamics. But from first principles, typically what people just do is look at things like a low sample estimation of the enthalpy. The second application is solar thermochemical hydrogen generation, where we basically reduce and oxidize a metal oxide at really high temperatures to produce hydrogen. Experimentally, of course, we can do this. First principles, we definitely don't predict these production rates as a function of time. You see here, the best we typically do is compute delta H of the oxygen vacancy formation energies. So the ultimate problem is that it takes, next click, is that it takes months to make these materials. It also takes months to just predict a proxy of performance for a small number of materials. Next. So traditional materials discovery is irreplaceable, but it needs to be augmented and accelerated. Depending on the experiment you're running, it can take days to years, of course. And typically that's been done through intuition that drives synthesis, characterization, and testing. Of course, the second kind of paradigm came about when we were able to have high performance computers where we could develop first principles theories to run simulations and predict performance. Those can also be fast, but they can also be intractable, right? And then machine learning tries to bridge this gap by, one more click, by taking data from experiments or physics-based simulations to train surrogate machine learning models, which the training process can be difficult, and you have to develop some, model theories on how you want to build your machine learning models. But ultimately, the goal is to, of course, then run these property predictions on the order of seconds or faster. So we look at a lot of materials at Sandia for hydrogen energy. Some of the things we touched on are metal organic frameworks, high entropy alloys, liquid metals, and metal oxides, kind of split between storage and generation there. The common theme is that there's tens of thousands of candidate materials, and use machine learning to reduce the number of materials that are considered promising by several orders of magnitude, that basically shortlists things that you can then take over on chemical intuition to choose the final number of materials you actually want to test in the lab. And so we'll be talking about high entropy alloys and metal oxides today. So I'll go through three sections. One will be about hydrogen generation, where we're looking at accelerated screening of oxides for Stitch, but more generally, the lessons learned will be applicable to other high temperature clean energy applications as well. Click. The second one will be looking at trying to find what I'll call Pareto-optimal high-entropy alloy hydrides. And then the final part is actually going to completely diverge from the data-driven materials discovery and look at how important it is to just integrate experimental data with systems-level modeling. So, and I'll talk about why we're interested in that, even though this is like a data-driven materials discovery talk. Okay, so click. So let's jump into the first part. So again, we're looking at basically what I'm going to call defect graph neural networks to accelerate the screening of these oxides. It's a national lab collaboration, including some work from people at Brown. And the key concepts are that we're going to use graph neural networks to directly predict relaxed vacancy properties from a host crystal structure. And if you can do that, you can high throughput new materials to predict this quantity and ultimately try and identify new materials that can do water splitting, operate as fuel cell cathodes, do CO2 conversion, and even thermochemical energy storage. So Stitch is one of the several prominent pathways to create green hydrogen or CO2 emissions-free hydrogen. So again, I briefly alluded to this, but the way it works is that you have a really high temperature solar receiver. That's actually a picture of the solar tower at Sandia. It's kind of not one of a kind, but not the usual thing that most people have access to. You go to really high temperatures to reduce the metal oxide and liberate oxygen from the lattice, and then you expose it to steam, still at high temperatures, but you then produce hydrogen. So the issue is really that nothing has been commercialized here in terms of Stitch hydrogen production. And that's because no metal oxide yet meets the requirements for a sufficiently low thermal reduction temperature, it's sufficiently stable, has fast enough kinetics, it's cheap enough, all these different issues. But there are some candidates that are pretty high performing. So one material that's been looked at extensively at Sandia is this BCM12R. Structure, and you can see on the right, those are actually pretty decent hydrogen production rates. But again, it takes months to identify a new material, and if you're randomly guessing which metal oxide might work for this application, you're going to be in trouble. So people typically turn to DFT, where they compute the oxygen vacancy formation energy, and we generally know that there's like a sweet spot that basically if that value is outside a range of 2.3 to 4 eV, it's not really worth looking at. So typically, we need at least one vacancy formation energy in that range. We want them all to be above 2.3 eV, because if you have anything lower, it's going to be too hard to reoxidize. And again, this takes months to compute this proxy for Stitch performance for a reasonable number of samples with DFT. So next slide. So this is my fun aside of the presentation. If you watch Blade Runner, the detective flies in the beginning of the movie across these expansive solar fields in I guess what's outside of LA, and this is this dystopian future movie, right, where clearly it seems like they didn't solve the Stitch problem or any kind of solar energy problem. So we don't want to be like Blade Runner. Next slide. So Anuj is my collaborator at NREL who does the DFT on this. So again, if we're looking for oxygen vacancies in this critical range, we rapidly encounter computational barriers. So go ahead and click. So he's screened a wide range of material space. That's kind of those green half triangles, but in reality, we want to look at basically anything that's also in yellow. It's a really hard problem because the DFT is not simple. You need magnetic sampling for these correlated materials. You need to do all sorts of difficult DFT calculations. So if you click, when this project started, it took him about a year's worth of work to compute about 1,500 defects in around 200 binary and ternary host structures. But if you look at the materials project in terms of available oxide space in this in this orange color coding, there's up to tens of thousands of materials, up to century compounds, millions of defects that you would have to relax. So completely intractable. So one way to get around this is, of course, developing surrogate models to predict this. Again, if you click once, the key challenge is really that beyond the magnetic sampling, you also have to create these really large supercells so that defects don't see their mirror image in a particular simulation, and then you have to do that relaxation of a supercell. And so if you have a lot of unique vacancies in a crystal structure, you have to do lots of supercell relaxations to characterize the material. So as a graph neural network surrogate modeling strategy, we interpret a material as a graph. So this is kind of, this graph neural network kind of got popularized maybe 5 or 6 years ago with the Xi and Grossman paper. And so we are drawing heavily from that paper where we basically encode a material as a graph, and you can see just a schematic of the feature vectors associated with each atom in that graph. And then you just perform convolutions. So we're not going to get too much into the math, but the point is that based on the bonds that you draw on the crystal structure and the geometry and the neighbors that you concatenate over, you can basically update those feature vectors for a particular atom through deep neural network layers. And then at the end of your convolutions, instead of doing a pooling where you basically sum all the information together across each individual feature vector, you just pluck out that particular feature vector associated with each atom in the crystal structure. So it's called node pooling. And then you run those through any kind of final feed forward layer to directly predict the vacancy formation energies for each site in the crystal structure. So the pros are that this is a generalizable approach. It doesn't rely on the fact that you have to do any kind of manual feature engineering, and that inherently makes it agnostic to the chemistry and structural space. You can improve this with more data, and it's many orders of magnitude faster than DFT. On the con side, it is also highly data reliant, right? So you're not going to be able to expect that you could predict nitrogen vacancy formation energies if you only provided training data on oxides. And it's not really interpretable, unlike other methods out there like linear models. They are built on physics-based descriptors, so what comes out is actually kind of interpretable, whereas here, for now, this is essentially a black box prediction. Next. So we have validated this approach for high throughput screening metal oxides. So on the left there, you're seeing the kind of the training curves as a function of size of the database, where blue is the expected error on cation vacancies and red is the expected error on oxygen vacancies. So we kind of stopped when we hit our benchmark of around 0.5 EV, but you can see we still have this log linear decrease in prediction error as we increase with more data. So there's definitely room to keep improving the models as we add more data. It doesn't take very long to train on a CPU. You could do it on your desktop if you wanted to. We typically train hundreds of models for cross-validation, so we still do it on an HPC, but if you just want to train one model, you can easily do this on your desktop. And then again, on the right is the parity plot, just showing that in general, you can pretty reliably predict both oxygen and cation vacancies. So then the question becomes, because we only tested on binary and ternaries, what does this approach do on more complicated materials than it was trained on? So on the top is just showing this BXM material, which I mentioned earlier, just showing that the DFT and the machine learning models are in pretty close agreement. And then on the bottom is a different class of material called a solid solution, where basically you have disordered cation sites. This is the SEM material, which is known for its water splitting capabilities, and just confirming that the GNN, even in this, when the range of enthalpies is pretty close, the model can still correlate within that particular structure. And most importantly, it captures the fact that the vacancy formation energy increases as you increase the cerium content in these solid solutions. So that gave us the confidence that we could go ahead and start screening new materials. So because of the data that was actually in our training data, we could only screen about 2,000 oxides out of the tens of thousands of oxides that exist in the materials project. That corresponds to 50,000 unique defects. One thing I didn't show here is that we confirmed that the model does not predict well on new crystal structures that contain cations that weren't in the training data. So that's why we're kind of limited to only 2,000 oxides for now. But then in terms of realistic, selection of new materials, there's a lot of things you need to consider, right? So I mentioned that we first want to look at the fraction of defects that are greater than 2.3 EV. They all need to be above 2.3 EV. And then we need at least one defect in the critical range. Nominally, you might want more than one defect in that range. And then the big thing that we also looked at was, what is the material stability? So going beyond just looking at energy above the hole, you have to also consider the host material stability as a function of oxygen chemical potential, because stitch is kind of relatively confined to this narrow oxygen chemical potential range on which it operates. So you basically need to confirm that the material stability in the grand canonical ensemble, right, when it's open to an oxygen chemical potential, is that the material will be stable and that range intersects the target range for stitch. Okay, so if you do that, you can screen all materials project. This is just showing the general correlation that everyone knows about who works in this field, is that the defect formation energy is in general correlated with the formation energy of the host crystal structure, but that's far from, you certainly need to be able to predict each defect in the material, because I'm just showing in the blue there one material where there's a huge range of oxygen vacancy formation energies, and you would need to toss that material out of your down selection. Next. So, we apply these increasingly strict down selection criteria. You can start with, anywhere from maybe 200 materials down to only 10, depending on how strictly you apply these stability and defect range criteria. So we increasingly filter certain candidates or that we think are good, potentially good water splitters. It mainly identifies known synthesizable host structures because we're, again, dealing with materials project, which is based on the ICSD. And a lot of materials popped up that weren't in the typical suspects. Not a lot. Some materials, popped up that weren't the typical suspects of AbO3 perovskites, Ruddleson popper phases, mixed metal ferrites, etc. And so this screening process rediscovered new materials. So BCM was a crystal structure in materials project. It rediscovers it as being, a potential water splitter. And, we've now identified new ones that the experimental team is working on. And they do have a manuscript in preparation on some of the materials that they've looked at based on this study. So hopefully I've shown you that, this kind of data-driven approach can make the rapid identification and synthesis of promising hydrogen storage materials tractable. So we, can screen any number of oxides. The machine learning model, execution-wise, is extremely fast. The DFT would take an intractable amount of time to screen the same amount of space, and then we use that to down select materials and perform new experiments. So what's next? There's a lot of interesting avenues for future development. So in the follow-up work, we're working on expanding the elemental space covered by the training data, and potentially looking at mixed data types. So here's the database of new materials. So round one is what we trained on originally. We've got a new chemistry, new structural space in this list. And I'm also interested in seeing if, there's ways to do multi-fidelity models. So we could use like Rob's calculations with scan plus U and integrate that with, our DFT data, which was calculated with GGA plus U, for example. Look at more structural diversity, and then also combine the best of both worlds. So I mentioned GNN has advantages and disadvantages. The linear models, for example, that Rob has worked on has advantages and disadvantages. So if we can kind of marry the best of both worlds for both of those, it would be really cool to see how much more progress we can make. And then as I mentioned, we have an LDRD. Kind of what that's focused on is going to more complex defect properties like interacting vacancies and substitutions, kinetics, etc. And I'll just mention that, so right now we're only predicting, vacancy formation energies. If we can do some of the things that we hope to do in the LDRD, we can predict the full phase diagrams and high throughput. So this is work done by a postdoc in our group, Pinwin. So he's a thermodynamic modeling expert. He's developed this automated workflow. It's very complicated. I'm not going to go through all of it here, but this is basically a way to take a crystal structure, DFT calculations, and experimental data and turn that into a phase diagram. So if you click next, the output of that whole workflow is essentially the ability to predict the oxygen off stoichiometry in a material as a function of the temperature and oxygen partial pressure. So you say, I operate my reactor between these two conditions. This is the amount of oxygen we remove from the lattice, and therefore, how much hydrogen we can produce in this thermochemical cycle. So this is only as fast as the DFT for now, but we look, hopefully we can integrate that whole process with the machine learning if we can, further increase its capabilities. Okay, so shifting gears to part two, we'll talk about hydrogen storage, specifically hydrogen storage in Pareto-optimal high-entropy alloys. So the key concepts here, we're actually going to first take a step back from graph neural networks and look at kind of simpler statistical learning models and show that that's a great way to do high-throughput screening and direct synthesis of destabilized high-entropy alloy hydrides. And then we're going to shift gears and go back to GNNs to try and solve some of the shortcomings of that approach. So the first thing that we worked on was just showing that kind of these simple, off-the-shelf, explainable machine learning models could predict metal hydride thermodynamics. So quickly again, I mentioned what a metal hydride was. I'll just quickly recap. So you have a metal and you expose it to hydrogen gas. The hydrogen dissociates at the surface and then migrates into the bulk. And that a useful hydride material is one that undergoes a phase transition so that basically you have an alpha to beta phase transition, which results in this plateau you see on the right in this pressure composition temperature space. So basically between a very small pressure window, you can release a lot of hydrogen. So, the way that you predict that that plateau pressure is if you know the enthalpy and entropy of that phase transition. And this is all data that's been accumulated over the years. So Sandia has a very strong, hydrogen storage program going back many decades, and luckily for us, someone or some people, accumulated this CSV file of, hundreds of, actually thousands of metal hydride papers, and did this analysis where they extracted delta H and delta S. The issue is that it was done, of course, pre-machine learning days, and it wasn't done, in any kind of, with any thought of like, oh, this needs to be used for a machine learning model. So there's lots of duplicates, lots of errors. After cleaning, you only have a fraction of materials left. Kind of relegates you to the world of like gradient boosting trees and random forest rather than deep learning, but that's okay. And just FYI, this is all on Zenodo now, and we're updating it continually now with some more standardized data reporting. So anyone who's interested can find this database online. Okay, so the way that we went about building machine learning models is just to build a simple compositional model based on MagPi features, which was by Logan Ward a couple of years ago, where you basically take the composition, you take the elemental properties in that composition, and then you just take the elemental fractions in that composition, and you derive a feature vector based on simple mathematical operations around those composition-weighted properties. So I'm showing as an example the volume per atom. So that's the volume per atom of the elemental solids weighted by its compositional fraction. That's how you compute this new PA value, which I'll re-reference a few times. So, if you just train your simple gradient boosting tree model off the shelf, it can actually produce this log equilibrium pressure with reasonable accuracy. Sometimes I'll mention it as delta G because the equilibrium pressure is just essentially delta G. And, so you can predict that within, that log value within a value of around 1.5. So pretty decent at, correlating metal hydride stability across the wide ranges that these materials can exist. And what's important is that, you have some interpretable insights, especially if you're using something like gradient boosting trees or random forests. There's no reason you shouldn't just apply these post-analysis methods like SHAP, which basically tell you how the model outputs depend on the input features. So the SHAP value there on the x-axis is the contribution of a feature to the model output, and each bullet point is an individual training example in a data set. So for new PA, you can basically see that, yeah, if I have a high value of new PA, I have a low value of the equilibrium plateau pressure. Basically, for that, it's basically a log linear correlation with new PA, and then there's other secondary features that tweak the prediction from there. Next. So we can predict destabilized high entropy alloy hydrides. So what is a high entropy alloy? It's essentially a solid solution on a well-defined lattice type with a large number of elements. Some people say typically are greater than 4, and that there's random site disorder on that lattice. So people have been looking at high entropy alloys for a bit now for hydrogen storage. So even if you take a relatively small elemental space, as you see there's 672 equimolar compositions. So you definitely need some kind of efficient surrogate model if you want to get an idea of their hydriding properties. So because we're working with solid solutions, we don't want to just predict any random composition, of course. We want to make sure that composition is likely to actually form a solid solution. So luckily there's, Miracle and Senkov, who kind of are some of the founders of this high entropy alloy field, published this really nice review where they kind of summarized which experiments have been able to isolate solid solutions of these particular compositions. The negative examples where they crashed out into intermetallics, or whether there was some phase impure mixture. So you can, again, train something like a gradient boosting classifier to get within a 75% class weighted accuracy, whether a particular composition is likely to form a solid solution. For those people who know about the Hume-Rothery rules, this is essentially just the Hume-Rothery rules, what this model is learning. But it's a way to make sure you're only predicting on materials you think can actually form a solid solution. Okay, so once you have that, you can go ahead and predict the log equilibrium plateau pressure. In blue is the original material that kicked off the interest in high entropy alloy hydrides, synthesized by our now collaborator Martin Sahlberg at Uppsala. Got everyone pretty excited because it had a massive hydrogen capacity. The issue you can see there is its log equilibrium pressure is extremely low. So what that essentially means is that you have to go to extremely high temperatures to desorb the hydrogen. So it's not really, we don't really think it's practical for actual real world applications, but it's a really interesting fundamental example that we need to learn from and figure out how to destabilize it while also keeping high capacity. So, you can screen all these new high-entropy alloys, and we chose 2 that kind of span the range. You can see that the predicted range spans many orders of magnitude, so we kind of just picked 2 in the middle. Also ones that included aluminum because it was just interesting. All right, next slide. So then we turn to our experimental collaborators who do all the synthesis. They do all the hard work, really. They do the synthesis, the characterization, and the PCT tests. So these are SEM EDS images of one particular high-entropy alloy we predicted, showing the fact that you don't have this elemental phase segregation before and after hydriding. So essentially, what was a high-entropy alloy is still a high-entropy alloy after you go through the hydrogen cycling. Go to the next slide. Then you measure these materials. Again, here are the PCT curves. Those are that massive increase in the plateau pressure is corresponding to the materials we predicted on the previous slide. If you click again, there I'm just showing that essentially the machine learning model did reasonably predict the new equilibrium plateau pressures for these compositionally modified entropy alloys. And on the right is actually that the equilibrium plateau pressure versus that new PA descriptor, which I mentioned, which has a log linear correlation. So again, it kind of helps also validate the machine learning design rule, the first order machine learning design rule. And so we've been using this a lot recently with our experimental collaborators to target basically known high entropy alloys that seem promising, but are basically their delta H's or their equilibrium plateau pressures are still too low. So it's turned out that this model is actually pretty good at predicting the shift in thermodynamic stability of these materials as a function of composition. And I won't get into all the details of all the different systems, but we've been using it pretty decently. Okay, so if you click again, I want to dive into these SHAP analyses briefly. So we added in some additional, hydrogen-specific features. So if you take like the binary hydride formation enthalpies computed from DFT, you can well define this new descriptor for any new composition. And besides just predicting the log equilibrium plateau pressure, we can predict the different properties of metal hydrides too, right? So we can predict their saturation capacity on a hydrogen to metal basis, and we can predict the enthalpy, just the enthalpy, right? So now we're kind of ignoring entropy for the moment. And when you look at these SHAP analyses, if you click one more time, interesting things happen. So if you look at a capacity from a perspective of capacity and enthalpy, they both have similar qualitative dependence on the same features, right? So mean electronegativity and mean binary hydride formation enthalpy produce the same effect on delta H and and H to M, but we don't want that, right? We want to be able to reduce delta H and increase H to M simultaneously. So this feature interdependence is actually physically motivated, and it actually produces what you see on the next slide. Yeah, go ahead. So where we actually can plot these interdependent properties next to each other. So we're now focusing on looking at Pareto optimal high entropy hydrides. So in general, having a useful metal hydride isn't as simple as just predicting the equilibrium plateau pressure. There's many design variables that you might want to maximize. So in this case, we're looking at trying to get delta H as close to 27 as possible. We want the highest possible volumetric capacity, and we want the highest possible gravimetric capacity, and the least expensive raw materials, right? So I can't show all 4 dimensions on one plot, but if you look in this plot here, I'm showing the enthalpy target and the H to M target. And you can see that, of course, the machine learning captures that as you destabilize the hydride and you get delta H as close to 27 as possible, you lose capacity. Just a well-known and unfortunate physical limitation, but that because you can formulate the problem this way, you can identify the Pareto optimal materials. So that's all the materials on this graph, essentially, in which no 2 properties can simultaneously be improved by switching to another material. So as long as we're operating on this Pareto boundary, we're essentially guaranteed to be predicting an optimal material for a particular use case, and that's why we've kind of focused on that in this subsequent study. So you can see some of the materials we've tried to make. It reduces the screening space of possible high entropy compositions from equimolar compositions from 20,000 by many orders of magnitude to just 100. So there's only really 100 on that Pareto front. So again, a manageable number to actually select for experiments. And then we passed them over to the experimentalists. We decided to focus on magnesium high entropy alloys just because magnesium's all in and of itself is an interesting hydrogen storage material, but it's interesting to see how it behaves when it's alloyed in a high entropy alloy. So we targeted new materials. We generated promising high capacity candidates. And we got the correct trend as predicted by machine learning between delta H and hydrogen to metal ratios, and the correct trend between the magnesium high-entropy alloys and their non-magnesium containing counterparts. But unfortunately, these ones are basically on that right side of that plot, so their delta H's are still too high to be practical for real-world hydrogen storage. So we got to essentially move to the left on that Pareto front in the next round of materials. So that's one way to look at this problem. But you might be wondering, well, that's a pretty simplistic prediction to take all the information contained in the PCT curve and just simplify it down to scalar values. And you're right, there's a lot of issues with that. So compositional models, first of all, they're limited by, or hampered by limited experimental data. And the bigger issue is that accuracy on significantly out of training distribution materials is unlikely. And we're lacking key properties of the phase diagram, like potentially the reversible capacity, the width of the plateau, as well as whether other secondary effects happen that we're not so excited about. So previously, we just suggested a composition, looked at the compositional model, used that to predict phase stability and these thermodynamic properties at a coarse level. But the new approach would really want to be able to suggest a composition, and through DFT be able to predict the phase stability of that particular composition and as a solid solution in these different lattice types, and then also probe the hydrogen absorption energy landscape. And if you can put both of those together and predict both of those with a graph neural network model, for example, you could actually, in high throughput, through high throughput sampling, come up with a more first principles, not only alloy stability prediction, but actually regenerate the hydrogen PCT curves. So now we're going to go switch gears back to graph neural networks. And this shares similar themes to the previous graph neural network approach, and I'll kind of go through that here. So again, we're taking a crystal structure directly as input. We're encoding it in a graph. We're performing convolutions and neural network feed-forward neural network layers to update that graph. And then ultimately, what we didn't do before is we didn't pool, right? We took individual nodes from that graph and passed that through a final layer to predict defect formation enthalpies. If you pool all the information, aka you add it or you average it, or you do a max operation, then you can derive this feature vector, which now describes the entire crystal, and you can use that to predict something like the formation energy. So that's exactly what was done in G's first papers predicting formation energies. So the issue, though, if you want to do thermodynamic sampling and predict phase stability of these alloys, you of course can't be using the DFT relaxed crystal structure. So if that's your input to the neural network, it's essentially a useless model because you already have the answer, right? You already have the DFT formation energy. So we need our model inputs to be based on the ideal lattice structure. So if you map all your atoms to some idealized FCC representation, you can do the site disordering and screen essentially millions of random HEA configurations, so long as you can predict what the relaxed formation energy should be from that idealized structure. So that's exemplified in the next little section here. So there's a DFT relaxed configuration. There's this idealized FCC representation mapped to its ideal coordinates. And when you try and predict a model or train a model to predict the relaxed formation energy, using either as inputs, both can predict the formation energy very well. So in this case, because there's not a huge rearrangement of the atoms, there's just local distortions. The model is able to accurately predict what that system should relax to based on the idealized input. So another thing I want to comment is that GNNs also, using this idealized representation, have surprisingly strong generalization capabilities. Oh no, that's not displaying properly. Well, that's unfortunate. I'll just try and say briefly that basically, if you train a material on only equimolar configurations, and then you screen it on non-equimolar configurations, that GNN is able to predict formation energies outside of the range on which it was trained. So it actually can identify more stable materials than it's ever been trained on, and when you shift to non-equimolar compositions. So it's a pretty important thing in order to build phase diagrams. All right, next slide. Okay, so this is what I mean by that. So on the top row, I'm showing the predicted formation energy distributions for a variety of compositions in this low density alloy space. of aluminum, lithium, magnesium, tin, and zinc. And if you go ahead and click, Rob, what really matters for predicting alloy phase stability is the energy above the hole, or essentially what, if you look at all the possible decomposition products of that particular composition, how much higher in energy is that material? So the unfortunate thing for this particular system is that you basically see on the bottom there that it's in the 50 to 100 MeV per atom range. So basically there's nothing in this compositional space that is going to actually be phase stable. So it's not going to be useful, I mean, for any application, right? You'll never be able to isolate this FCC alloy. And this is, you know, we originally looked at this because there's an interesting paper that was trying to synthesize these low density alloys, but couldn't, and kind of just speculated, you know, from experimental results why that was the case. And if you do an exercise like this, you can clearly see there's no hope of ever making the material. So, you know, we can reduce the energy above the hole by playing, you know, around with it in the compositional space, but no matter what, we're still on the high side of the metastable synthesizability limit. So pretty much no hope. And this explains why you can't make this material. So we kind of wanted to look at an exotic hydrogen storage material to begin with, but we decided that was maybe not the best approach. So we turned to a more classic hydrogen storage system to show this approach for, it's not just applicable to alloys, but to hydrides. So if you click, you know, this ideal FCC lattice representation can also contain interstitials in it. So you can just put hydrogen at the possible binding sites in the material. We looked at palladium alloys. And so these are the test set predictions for the different palladium alloys across the hydrogen absorption, possible hydrogen absorption range. You can see, again, the GNN is quite accurate at predicting the relaxed formation energies from this idealized representation. And again, like this is kind of comments on the extrapolability a little bit, which unfortunately didn't show well in the previous slide. But these green stars are random configurations for a particular hydrogen density that were identified as being lower or higher in energy than anything it was trained on. And then if you put those back into DFT, you get qualitatively the right results that, you know, indeed these energies are lower than anything or higher than anything that the model's been trained on. So this slide's a bit busy to get into too much of the details, but I wanted to emphasize that in order to do the thermodynamic predictions, you need to be able to screen tens of thousands of configurations. So this color-coded density in the back is essentially all the machine learning predictions. And the solid lines in the middle are the average of those formation energies as a function of hydrogen content. So you can see if you use DFT, that's essentially the orange and black lines, you get a lot of noise in your signal, which adversely affects your ability to predict the PCT curve. But in red, if you actually are able to, you know, screen tens of thousands of configurations, you can completely converge these distributions. And that's what's ultimately going to allow us to predict the PCT curves. So yeah, in reality, we screen millions of configurations for this. So that gives us the ability to compute the PCT curves. On the left are just kind of a simple thermodynamic formalism that is surprisingly works pretty well for predicting the PCT curves in the system. So you assume an ideal mixing entropy, you can write out the Gibbs free energy, and the energy term comes indeed from that GNN sampling that I showed on the previous slide. And there's multiple ways you can do that. You can do a mean field theory approximation or a Boltzmann sampling. But if you have that and you fit the Gibbs free energy to a polynomial and differentiate with respect to chemical potential, that gives you the pressure, and then that allows you to construct that PCT curve on the right. So the critical things that we see are that we're able to correctly rank the plateau pressure, again, spanning many orders of magnitude in the palladium hydride system. That happens when you notice how small of a fraction you're actually doping of rhodium and silver, for example, and that produces many orders of magnitude increase in the plateau pressure. What's also really interesting is that the model correctly gets the saturation capacity ranking correct, and this goes against what I just said, right? In this system, the less stable the hydride, so the higher the equilibrium plateau pressure, the higher the capacity. So this actually goes, this system actually goes against the general trend of lower capacity for less stable materials. And then if you can, of course, you know, do this prediction at different temperatures to elucidate the phase envelope and predict the reversible capacities on the right there, or essentially the plateau widths. So we've been trying to apply this to more complicated hydrogen storage materials. There's still a lot of work to do, mainly because this thermodynamic formalism has to get a lot more complicated when the interstitial geometries get more complicated than they exist in the palladium FCC alloy. All right, next slide. So the last thing that I'll touch on pretty briefly here is the importance of doing material and system co-design to truly optimize metal hydrides for real-world hydrogen storage applications. So now I'm actually going to throw out all the data-driven work and just focus on experimental results and how they combine with systems calculations to evaluate material performance. So one thing that that Sandia and Mark and Vitaly actually have been working on for quite a while, even well before I even joined Sandia, is nanoscaling of metal hydrides in nanoporous hosts. So if you click, Rob, so one particularly interesting example of this is confining lithium nitride in a nanoporous host. So you get a lot of benefits from doing this, which we don't have time to discuss, but you significantly destabilize the reaction. So that's great. Lithium nitride typically hydrogenates with a delta H on the order of 70, which is way too high. And you get it all the way down to the 40s by doing this nanoscaling. In the middle there, you greatly improve cyclability of the material. So that's a really good number of cycles for a complex metal hydride there in the middle. And there's been a lot of theory work that kind of looks at why these are the cases, and it's very complicated, but it gets down to the fact that you form favorable nanointerfaces and this kind of core shell hydriding structure that kind of synergizes to make all these great benefits. Okay, so what's the drawback? Unfortunately, when you do this nanoscaling, you improve a lot of properties that are really important, but you also hurt a lot of properties that are important. So these 5 properties here, the hydrogen weight percent, the thermal conductivity, the density, and the enthalpy and entropy of hydriding are the 5 key properties you need to know to be able to size a hydrogen storage tank, for example, for a light-duty vehicle or a heavy-duty vehicle. And you can see that some things are negatively impacted by this nanoscaling, right? So the first thing that's obvious is you have a 25% reduction in the gravimetric hydrogen capacity. You have an amazing increase in thermal conductivity, 400% increase. You have a reduction in the density. You have an amazing decrease in the delta H, but you also have a decrease in the delta S, which is bad. So the question is really which material is actually better for hydrogen storage. And the only way you can do that is by having access to a systems model like our collaborators at PNNL produce. So Kristen Brooks has been leading this effort, as well as others. But he basically developed these systems models that allows us to determine determine the system requirements to store a certain amount of hydrogen, right? So it accounts. The key thing is that it accounts for all this balance of plant you see here. You have a heater. You have to have a heat exchanger in the metal hydride bed. You have to have the balance of plant to move things around. And so if you click next, what happens is that if you put all that in to this design tool, you can actually evaluate how much usable hydrogen you get per system volume or per system mass. So the bulk materials on the left, the nanoscale materials in the middle, and 350 bar compressed gases on the right. And that bottom row is the volumetric systems capacity. So the nanoscale material actually does better than the bulk, despite it having a significantly lower gravimetric material capacity. And this mainly comes from its increased thermal conductivity and its decreased delta H. So you got lots of really interesting insights on that. And while this material isn't able to beat 350 bar, the Sandia experimental team, I'll just mention, is working on a material that will compete with or be better than 700 bar in these vehicular applications. So that's a pretty exciting result. And again, the only way we know this is because we can put in all these fundamental material properties and get a systems calculation out. Okay, so that just, what I've talked about just does the sizing of the tank. The original Hydrogen Center of Excellence developed a full-scale MATLAB vehicle simulation code to then take that sized system and see how it would behave dynamically under a simulated vehicle drive cycle. So this is the kind of the make or break, right? Does the material actually perform as it needs to in the simulated drive cycle? So in solid purple there is the nanoscaled material, and it's the tank pressure as a function of drive cycle time. So that rapid decrease around 100 seconds is coming from the fact that you have to burn a lot of hydrogen to heat the material up so that it can release more hydrogen. But it is able to do that and then continue on its way and finish the drive cycle. The bulk material, you can see how much faster it depletes its hydrogen in the tank headspace. It has to use all of that hydrogen up just to try and heat up the bed. And at the end, it uses up all the hydrogen. It never got the material to a high enough temperature. It can't release any more hydrogen, and then the fuel cell dies. So these are the kind of critical insights that we need from systems design. And I wanted to point this out because all of these things that we mentioned in the materials that you need, or the properties that you need, we can only predict a handful of them with data-driven, or even just theory in general, right? Some of these things like thermal conductivity, the pelletized density are extremely hard to even think about calculating from a first principle standpoint. So kind of just grounding us in the fact that what we can predict is still only a fraction of what we actually need to truly evaluate materials performance in the real world. Okay, so concluding remarks. Go ahead, you can just click through these, Rob. So yeah, we've shown that data-driven materials discovery efforts can take on many different forms depending on what data you have available, what are the constraints of the problem, what type of data you have, things like that. Hopefully, I've shown that there's a lot of open area for discovering new and improved hydrogen storage materials, and hopefully we can help accelerate hydrogen deployment by discovering them. I think understanding the efficacy of high entropy materials is really critical, since a lot of people tend to be turning to them in a lot of areas. And the explosion of possible space that you have when you deal with high entropy materials means that we're really going to need data-driven insights to drive efficient experimental progress. And kind of the sobering final takeaway is that if you ultimately want to predict how a material is going to behave in the real world, you basically need a systems level model, which is very very difficult to build and takes a lot of time. And really beyond that, you have to do the experiments. There's just some properties that go into them that are just going to be incredibly hard to model, let alone in high throughput. So with that, thank you for your attention. Always happy to answer any questions here or by email.